Gentlemen, good morning. What kind of coffee are we drinking? Kurt, Matt, show yourselves.
Ethiopian Yogurt.
I am actually drinking an instant coffee that is an Ethiopian also that is really delicious. I'm really surprised that it's good. I was expecting like Yuvan, but it's not. Matt, what do you got?
I'm still working on the same bag of Colombian from Black and White, so still sipping on the same stuff.
I actually had Black and White. I was really impressed with their roasts.
Yeah.
Mr. Benedict.
Working on some two-stitch from Unravel still.
Okay. Okay, let's
try
get
that. That was really good.
Huh?
Well, I was just out in Denver. I tried that. That was really nice.
Yeah, I want to get some Unravel. I've heard really good things about them. Okay, we've got a lot of ground to cover. Good morning, everybody. Welcome to Ask the Expert Session 4, Season 4, Episode 4, What a Tech Needs to Know About Electrical. My name is Hylan Joseph, and I'll be your moderator. This presentation comes from a series of in-depth webcasts between Michael Teahan, our presenter, and myself and Don Berquist of Ranchilio for Ask the Expert Pro. There's 6 hours that go with this webcast, and they will be posted on Slack in March. Today, our presenter will be Michael Teahan. He will present for about 30 minutes, and we will allow question and answers. The Ask the Expert Pro series for everyone. This is our second season. The season will consist of 9 episodes. We're committed to presenting these episodes throughout the year, so save Fridays at 8 a.m. Our standard introduction. This presentation is for informational purposes only. The views and opinions expressed in this webcast are those of the presenters and do not necessarily reflect the official policy or position of any aspects of the Specialty Coffee Association. We also want to introduce our CTG program, which we've been executing the first modules to the AST program. We want to tell you about the new Cofee Technicians Program. It's a standardized education curriculum that the Guild developed with the education department of the SCA. It consists of 6 different modules, and we welcome learners of all levels of experience to take this course. All of us in this meeting are involved, and if you have any questions, please reach out to the contacts that will be on the slides at the end of the presentation. We're happy to help. The panel consists of Matt Martin of VIXO, me, Hylan Joseph, the moderator, Michael Teahan, and Kurt Benedict. Let's get started. And Michael, why don't you quickly tell us about yourself, then we'll move on to Kurt and Matt.
I've been in the coffee industry for better than 3 decades now. I do a lot of training, I do a lot of tech support, was working with factories on compliance issues and how to make the machines not break. Unfortunately, didn't always work. But I've kind of been in and around everything and everywhere, it seems.
Matt, how about you?
Sure. My name is Matt. I've worked anywhere from being behind the bar in a variety of different locations to being a technician to now being a trainer here for VIXO. So I handle anything from training materials, development, training on units, and all sorts of things. So.
And Kurt, how about you?
Been working in the industry for about 8 years now. Or in the coffee industry. In service industry, I've been close to 20 years. It's been my whole career. Just like working with people, and I do on-the-job training mainly. I rely on people like Matt to give them the classroom training, and then I like taking them out into the field and training them to work on all the espresso machines and equipment.
Cool. So this presentation is about what does a new tech need to know about electricity. What Michael's going to cover is voltage, electrical safety, volts and amps equals watts, which is Ohm's Law. What is a short circuit versus an open circuit, basic wiring and plugs. Now, this is an incredibly broad subject that we've worked really hard to distill into a 30-minute presentation. So if you have any questions, feel free to ask as Michael is going over things, and we're happy to help. Michael, I'm going to turn it over to you. And slide 1.
Okay. We try to break it down into 5. Are we on slide 2 on the table of contents yet?
We're on voltage 101.
Right. For some reason, my screen isn't advancing. Hang on a sec.
No, I have it. I'm advancing. Oh, Mike, I'm doing it. So we're on voltage 101. So when you want to move screens, just let me know.
Yeah, let's move the screen.
Okay, you're on voltage 101.
Okay, my screen is not refreshing. Okay, I've got a hard copy in front of me, that's fine. Okay, so basically the way that AC current works when it comes to a building, and this is true for any application, whether you're in Europe, the US, it doesn't really make any difference. Electricity is a wave. Don liked to call it like a river, essentially, of energy that's flowing from, from the power generation source all the way to the point of use. And that waveform is how we essentially we kind of duplicate that, what DC current is. There we go. So there are two lines that typically come in the building, but we're going to talk about one first. So when the line comes into the building, it's coming in at a certain rate, which is about 60 cycles every second. And so it comes from a source of a spinning rotor, and that spinning rotor is spinning positive and negative and positive and negative, and it rotates at 3,600 RPM, which gives us the actual cycle wave of that waveform. So what happens is it's coming in, it's like the electricity, instead of flowing in one direction, it's kind of like pushing and pulling and pushing and pulling and vibrating. But to do any work, it has to reference some kind of ground or neutral. So when a neutral is introduced, then the waveform actually takes shape. And as it passes through positive and negative voltage, it forms that 120 volt AC curve. Now the voltage is actually a little bit higher, but because of the way we measure voltage, because the voltage is always moving, it has to kind of take an average. So typically you're going to get 110 to 130 volts coming into a building, but typically we just call it 110. So let's go to the next slide. And the amplitude of that wave is the actual voltage. So how high it is the actual voltage. When you introduce a second line, it's a second 110, 120 volt line. But you can see that they're out of phase. So the red line and the blue line are actually 180 degrees out of each other. So when one is peaking, the other one is in the shallow. And it does that because the pole is actually 240, and the pole actually splits it with the capacitor to delay one of those phases 180 degrees, much the same way that capacitor works on a motor for a grinder, for example. It doesn't store energy. What it does is it pauses the wave just a little bit. It's amazing to think electricity is actually this moving target. It's always moving. We tend to think that it's either hot or it's not, but it's actually, almost like a sound in a sense. But when you take these two waves, because they're 180 degrees out of phase, let's go to the next slide. Because most commercial machines are operating on 240 volts that come out of Europe. Go to the next slide, Hylan. Okay, so on the top left, if you remove the neutral and you're only working with the first line and the second line, the distance between those two peaks is 240 volts AC. And that's how we get that higher current. It's the difference between those two out of phase links. So when you remove the neutral, because there's no neutral, when there is a neutral in Europe, but when the machine comes over to the US, that neutral is gone. So we're only referencing the lines themselves, and that's how we get the higher voltage. So when you're actually measuring that voltage, well, how does the meter know what that actually is? So on the bottom right, you'll see when you measure it with a typical digital meter, it's actually doing a calculation based upon the sampling of the voltage as it's passing through the meter. And what you're actually reading is that black line. So when one is peaking, it actually peaks at 240 and then drops to 240 negative, but you don't actually see it that way. So you're actually just measuring the AC current as it passes through. So that's how a commercial espresso machine is able to get 240 volts out of two 110 volt lines. We're not going to talk about three-phase today because three-phase is pretty rare these days with espresso machines. Does anybody have any questions about this? I know it's kind of technical. It's kind of weird. We don't always think about electricity in terms of moving waves and sound, but that's how it works. Anybody have any questions so far? Nothing?
Kurt, Matt, anything on your end?
Well, can you explain for people, so you're talking about the 240N. Now, yeah, how does it work when you have, let's say, pieces or parts that are 110, or how does it get the 110 only? Can you explain that for everyone, please?
Right. So on brewers in the US, for example, you'll have, so there'll be like 240 volt heating elements or 208 volt heating elements, but a lot of the components are operating on 110. So in that case, you're actually supplying a plug, which we'll cover later, that actually has 4 wires to it: a ground, line 1, line 2, and the neutral. Because even though you're getting 240 volts between line 1 and line 2, if you have the presence of a neutral, you can still tap 110 between any one of those legs and neutral. So you basically have a dual voltage machine internally. A lot of brewers will run components at 110 because they can just make 110 volt components for everything and just tell people to provide a neutral. In Europe, it's a little bit different. They just say everything is 240, and work it out on your own. Because a 220 or 240 volt machine in Europe and most of the rest of the world does have a neutral. So a lot of these graphs actually apply. Double the numbers, if you will. So in England, you'll have 220 volts on one phase referencing neutral. But when you put those two phases together, you'll get 380 volts in a 3-phase application, sometimes more, as opposed to the US where you simply get 240. Okay, should we move on? Okay.
Yep, let's move on to electrical safety.
Actually,
Okay.
real quick before we get too far,
Yeah.
another one is what is actual ground? I think you touched a little bit on this subject, and what is actual neutral, just so it's kind of clear for everyone.
Okay. Neutral and ground essentially are the same, but they're treated differently. So if you look at under electrical safety, you'll actually see that green wire, that green line is actually the ground. That's the protection. So because back in the circuit panel box, the neutral and the ground are actually tied together. It's the same wire. So if you were to measure continuity with your meter between ground and neutral, it should read almost no resistance at all because it's the same circuit. The difference is that the neutral wire, because it's actually carrying a load back from the machine, it has to be isolated from everything else because it's always carrying some degree of current back, because that's the reference for the waveform. The ground wire is a protective shield around that, so that if any of those wires make contact with the ground, it causes a short circuit. Now, if any of those wires were to actually contact neutral, it would also cause a short circuit. But the neutral is actually something that's used. So by keeping the ground separate, it becomes a safety device. So one of the things about electrical safety is, everything inside an espresso machine, and in fact any machine at all that's got a UL listing or an ETL listing, every metal component on that machine is grounded with an actual ground wire, and that ground wire is strapped in. So when, for example, you take a panel off of an espresso machine and it happens to be metal, there will usually be a wire that connects that panel to the machine, so that in the event that any of those phase wires anywhere makes contact with the surface of the machine, rather than electrocute the operator, it's simply going to short the circuit and blow the circuit breaker. So that ground protection is kind of the overriding protection of the machine, because it's always easier for the current to go back through the ground, back to the circuit panel and blow the breaker than it is to pass through a person, because you have a little more resistance. So essentially neutral and ground are the same, but they must be kept separate for the machine to operate properly, and they must be kept separate. For example, if you've got a loose neutral wire somewhere in the plug, no, you can't simply run that to ground and make it work. At least you're not supposed to.
Let's move on to electrical safety. Mike,
yeah.
let's move on to electrical safety.
Okay. Well, that's what I was kind of covering in the electrical safety slide, that any contact between any of those lines and ground causes a short circuit. Now, that doesn't mean that, sometimes wires, I'll cover this a little bit later, sometimes there'll be a short inside the machine that doesn't blow the circuit breaker. And that's for it's in a very specific kind of scenario, and we're going to cover that later. So I think that we can move on to the next slide. Okay. From a service standpoint, one of the things that we have to worry about is safety. Are we going to die? Electricity has the potential of actually killing you. So we always have to be very, very cautious around it. Anytime a machine is plugged in, it needs service, it's a potential hazard. Now, the tricky thing about in North America is that in most of the rest of the world, when they run 220, 240 volts, they're running it against a neutral. And most of the switches and things like that inside a commercial espresso machine coming out of the rest of the world is only concerned about turning on and off that one hot leg. They don't really care so much about the neutral. But in the US, the way that we build that 220 volts is we actually have those two hot leads. So even while the espresso machine is only turning on and off that one hot leg, the other leg isn't turned on and off at all. It's always hot. That's why we have to be particularly careful. So whenever working on an espresso machine, obviously when you're coming in as a service agent standpoint, you kind of want to get a sense of what the machine is doing. Usually it's on. In the event that you have to start pulling body panels and things like that, unplug the machine before you pull the body panel. You do that because you don't know who's been there before you. You don't know what the status of the wires are. You don't know if there's anything loose that could be a hazard. And any body panel, if shorted, and not properly grounded, could pose a hazard. So when you unplug a machine? You unplug it if it's on fire. The reason why we have plugs is precisely so that you can unplug them. That's why you never, ever hardwire an espresso machine. You shouldn't hardwire a brewer either. You unplug the machine before you take off any panels, because as soon as you take off panels, that's when you're exposing yourself to potential high voltage. And while you're repairing any line voltage components, that means elements, pressure sat switches, limit switches, relays, anything that's got high current going to it, sometimes you can trust the switch, sometimes you can't. There's going to be voltage in there at some point unless you just unplug the machine. But there are circumstances when you have to have the machine connected. Obviously, when the machine is complete and you've done your repair and you have to test it. But some things, when you're testing trace voltage, you're trying to make sure that you're actually getting voltage to motors, getting voltage to heating elements, things like that. You do have to have the machine plugged in while you test it, but you have to also be careful. Make sure that the panels are far away. Make sure that whatever employee is milling around trying to service a customer is kept away from the machine. Wires can be long. You don't know what they're going to, they could drop a cup of coffee on it and make a mess of everything. So you need to have plenty of room to work. You have to think about what you're doing before you do it. You can't just jam a screwdriver somewhere inside a machine and hope that all is going to be good. So that's just basic stuff. But even as a veteran tech, sometimes you want to take shortcuts. Sometimes you just want to kind of get to it because you think you know what the problem is. But it's, once you've evaluated the machine, unplug it, then strip it apart, and then kind of figure out where you're going to go. Develop a game plan before you plug a machine back in. So let's go next. Any questions? I know that some machines have low voltage circuits, and if you've got an access panel for low voltage, that's fine. But generally speaking, just unplug the machine. Okay, this is a question that I get a lot from techs, like what can I do? So I've got a box here. This is a typical, installation diagram for an espresso machine. And you've got the machine, you've got the water softener, you've got water, drain, plugs, all those kinds of things. Anything inside this box with a green check mark is your territory. Anything that's inside that box, you can work on and probably should work on, because you have to attach plugs. You have to be able to fit the water line to the water valve. Anything outside this box is out of bounds. You cannot play with it. So what that means is that, for example, the plug you can rewire. You can make sure the plug is secure. You can plug it into an outlet. You cannot work on the outlet. Anything from the outlet all the way back to the electrical pole is not you. That's somebody else with a license, because you do not have the liability protection to work with high voltage behind the wall. I mean, generally, we kind of consider that the wall is the barrier. You know, anything on this side of the wall is okay. Anything on the other side of the drywall is no. You know, and that goes the same with water valves and gas valves. You can connect to a water valve, but you cannot replace a water valve, because that's what a plumber does. And the same thing, of course, with gas valves.
Mike,
yes.
I have a question. I hear this in the field a lot. Is they're working on a plug and they find that the plug, the female, is loose, but they can fix it. Do you think that they should?
No.
Okay. Why is that?
They don't have an electrical license.
Okay.
And I get that, and that does not mean that I have not fixed my share of plugs. But you know, if you're a sole proprietor and you don't really care what your insurance rates are, and you think you know what you're doing, you know, that's a judgment call. Generally speaking, you know, you're there to work on the espresso equipment. You're not there to rewire the building. If you want to get a license and change your rates, you know, to $200 an hour so you can work on electrical, then you can bill accordingly. But from the standpoint of, you know, your employer, it's not a good place to be.
Thank
Okay.
you.
Ohm's Law. Why do we need to know Ohm's Law? Generally speaking, math is not something we work on too much when working on espresso machines. But it's important to know when you're speccing a piece of equipment or trying to figure out you know, just how big of a heating element can you throw in a machine, to kind of know where you stand. And the power draw of a particular machine it's actually pretty easy to calculate. Ohm's Law is essentially, you know, volts times amps equals watts. Generally, when evaluating machines and trying to figure out how big they are and what kind of circuits they go on, we kind of reverse that. So if you take the power of the machine, let's say you got a 6,000 watt or a 5,000 watt espresso machine. If you divide that by the volts that are actually provided to the machine, that'll give you how many amps it's going to draw. And that amperage is going to tell you what gauge of wire that you have to specify to the electrician to power the machine. It'll also specify what circuit breaker the machine has to be specified for. It means that if you're going into a client who's upgrading from a 2-group espresso machine to a 3 or 4-group espresso machine, and they think they can simply plug it in, that's not always the case. And Ohm's Law is where we figure out whether that new machine is going to fit on that old circuit. And if you take in this example here, for example, in terms of the calculation, in the U.S. we get 200 plus volts in a variety of different flavors. We'll get 208 volts in some industrial applications because it's a derivative of a 3-phase application. In a lot of older neighborhoods or older buildings, you'll get straight 240. And here's the difference. You got a 4,000 watt espresso machine, but your voltage is only 208 volts. That's pulling 19 amps, which is just about the limit of a 20 amp circuit breaker. It's probably going to be okay, but it might blow that breaker at some point, especially if the wiring is in any way old or you have any issues. But if you're feeding with 240 volts, it only draws 16 amps, and you're much, much safer. And in the case of 5,000 watts at 208, that's 24 amps. That's going to have to sit on a 30 amp breaker. In some cases, if it was 240, it might just barely slide by on a 20 amp breaker. So Ohm's Law is a calculation that you use to figure out just exactly what you can get away with new equipment in a building. Any questions? Okay, shorts.
Actually, yes.
Don and
My practical uses of Ohm's Law when you're on a service. Give me 2 good examples. We had this on Facebook where we put out the Ohms circle, and everybody, I asked how many people used it. About 70 people responded that they did, but no one gave me good examples. So can you give 2 good examples of where it's practical other than elements?
Oh, I mean measuring ohms?
Yeah.
Or you can ohm out solenoid valves. A solenoid valve is a coil, and because a coil that develops resistance, that's how it develops its magnetic ability. So I'll use ohms to check solenoids. I'll use ohms to check transformers on circuit boards. I'll use ohms, of course, for elements. I'll even use ohms on probes, water probes, because I know that I should expect 600 or 700 ohms on the probe when it's passing through water. And if I'm not, that means that it could be calcified, or I've got a calcified boiler, or I don't have any water in the boiler at all. But in terms of using Ohm's law and doing the calculation, short of setting up a machine, I don't use Ohm's law that often. I used to do the calculation like on measuring an element. If it's got 14 ohms, you can actually kind of backtrack what the size of the element is if you know the ohms and the voltage and the voltage supplied. But I'm kind of lazy, and I'll just look at the side of the element. It'll tell me how many watts it is. The funny thing about elements, though, is that the resistance of the element, the actual wattage of the element will fluctuate a little bit when you feed it more voltage in terms of its power output. So resistance is a little bit.
Can you repeat that? You're breaking up.
Law. That's why on some menu. The resistance of the element will the heat output of an element will change a little bit with voltage. That's why on some manufacturers they'll list not just the wattage draw at one voltage. They'll provide a wattage draw over a range, depending on whether you're getting like 210 or 240 volts. But I figured that's a little more complicated than we need to be. So on shorts, you've got normal shorts, and you've got ground fault shorts, and then what Don Berquist refers to as open shorts. So a normal short circuit happens when any of the power lines makes contact either with another power line or with a neutral, or not particularly with ground. So for example, you can have a shorted coil where the coils are actually shorted together, and the coil no longer functions, but it's getting resistance, but it hasn't blown the circuit, because basically that resistance kind of forms a little heating element and it gets warm. It doesn't work, and it is a short circuit, but it's not evident because the circuit breaker is blown. You could have a shorted circuit on a board transformer, so the circuit board doesn't work anymore, but everything else gets powered, everything else is fine. You can even get shorted motor windings. And a shorted motor winding, for example, on a grinder, for example, you've got a start circuit and a run circuit. And that start circuit may be fried, and the motor will spin if you spin it up, but the short circuit itself has disabled it. Whereas a ground fault short is where one of those wires has actually touched the frame of the machine somewhere. And a ground fault short will generally throw a circuit breaker. An open short is simply a disconnected wire. So for example, you got a high limit switch that's failed and the heating element won't come on. That's an open short because it's not doing its job. You can also have corroded pressure stack contacts, for example. So even though they're coming together, they're not actually making contact. So in a sense, that's an open short. So you have cases where wires are touching things that they shouldn't, and you have cases where wires aren't touching things that they should. The only couple of exceptions, for example, on elements, an element can be fractured inside and will actually leak voltage to ground through the water inside the boiler, and it won't blow the circuit breaker. And it's doing that because the water itself is kind of becoming a heating element, and it's referencing ground. So essentially a 240 volt element now becomes a 110 volt element, but with massive resistance. So in that case, like the boiler will actually get warm, but it won't get hot. And because it thinks it's just trying to heat up the water, it's not enough to blow the element. So next, because we're getting close to 30. Okay, basic wiring. I tried to cover different colors for different applications because this is what you're going to see typically on the core of the machine. For European machines, blue is always neutral. And it's neutral almost everywhere else in the world where what you have coming out of the wall is 240 for everything. In the US, that blue wire actually carries current because we actually use that blue wire as the other leg to achieve 208 or 240 volts to the machine. So this is the one distinction where one wire kind of carries two loads. So if you're here from Europe, blue is always neutral. In the US, blue is always going to be connected to that second leg. Machines that are manufactured in the US, though, if they're buying cords from the US, that neutral is going to be white. And if they've done their job, they won't actually provide a power cord with a white leg, but that's the way it is. The other two colors you'll see on a commercial espresso machine are brown and black. Those are both hot legs. They're always hot legs. If you have a machine that's coming in that could be wired in three-phase, or we call it three-phase, with a blue, black, brown, and a ground wire, you can generally operate those machines in single phase simply by putting the brown and the black wires together in the same terminal in the plug. So then you'll have a blue and then a brown and black wire together, and that will give you 240 volts to the machine. The one thing the Europeans do better than the US is they put a green stripe on their ground wire for all of those people who are colorblind. In the US, it's just straight green. I've encountered whole circuit boxes full of green wires going into circuit breakers, and I think it was because the electrician was colorblind. And you'll see those green and yellow wires going everywhere. Wire is how many amps it can handle. Most of current wire in the US is actually pretty sturdy, solid copper stuff. And I just put a chart together. Okay, plugs. This is where I said it before. Plugs should never be machines should never be hardwired. The most important thing you can do with a plug is unplug it. If there's ever a problem in the machine, it's on fire, it's electrocuting people, it's overfilling, it's doing it's destroying a restaurant, it's about to explode, just yank the plug out of the wall. For most 110 volt plugs, for the most the smaller machines, the plug you're going to see on the left is what you run into. It's important that the neutral wire, the white wire or the blue wire, depending on how you're doing it, go to the neutral. And that neutral is a bigger leg. Sometimes it's silver. And the reason for that is because inside the machine, all the switching that it's going to do, it's going to be switching the hot leg. It doesn't want to switch the neutral. So it's going to expect that hot leg come from that smaller prong. And the same thing is, the same thing goes over to the larger plugs as well. So we've got two diagrams of plugs. The most common that you're going to see on an espresso machine is a twist lock plug, an L620 or an L630. The only difference is the size. The ground legs are always the ones with a little angle on them. That's so you can always identify them. And in case of the X and the Y, it doesn't matter which wire goes where. They're both. It doesn't really make any difference. You will occasionally find 4-wire plugs, especially for coffee brewers. And it's essentially the same thing as a 3-wire, like an L630 or an L620, but it actually carries a neutral as well. And that neutral wire is what allows you to provide 110 volts to various components of the machine in addition to the 220. The neutral wire is always opposite the ground, and the ground always has the dog leg. And that neutral wire, again, it really only applies to brewers. If you have a commercial espresso machine and you've got a 4-wire hookup and you don't have a neutral, I think it is acceptable to hook up the ground and the X and the Y and just leave the neutral disconnected because you're not using it. It's not going to impact the machine, and it's not going to pose any hazard to the building or the equipment. Any questions?
Matt, Kurt, you have anything? Okay, I think that's
I
the
do
last.
not.
Okay, gentlemen, log in. Let's see your faces and let's do question and answers. We have a lot of comments and we have a lot of questions. So what I'm going to do
I'm wrong about everything.
what I'm going to do, I have one comment I'd like to address from emailed to me, and then we're going to go through and we're going to deal with the questions first. And I'd like input from the entire group. The first comment that was emailed to me was, just to clarify, neutral and ground are not the same. We shouldn't confuse the two. The only place a neutral ground bond is allowed is in the main panel.
Yeah, I was trying to make that clear that they're because they're connected in the panel, you will get perfect continuity between the two, but they serve completely different functions. In the case of if you're working out of your house, for example, there are dryer outlets that are allowed to operate with 2 hot legs and a neutral. But it's a very specific application. Sometimes ranges are the same way. That they're able to utilize the ground and the neutral together in that application, but it's only because, you know, buildings are really old and they couldn't rewire everything. It was a special exemption. That exemption does not apply to espresso machines and commercial applications. But yeah, they're kept separate because they serve totally different functions.
Okay, thank you. From Nathan Van Duzen, my electrician tells me that we actually only get 208 volts on a 240 circuit. Is this true, and is it problematic for the health or the longevity of the equipment? Any of you can take
Anybody
this.
else?
Matt, you're shaking your head.
Yeah, I think that's in all the installs that we do in North America, like there's so many different concepts as to what 208 and 240 is and what that looks like. And as Michael was mentioning earlier, every building's going to be a little different. You might get a true 240 in one of them. You might get a straight up 208 in a different one, depending on what's going on. And then you have instances where you have like low legs and stuff like that too. So I think there's a lot of different options that could be happening there. They're different, but yet sometimes the same, depending on where you're located, I think. But Kurt, I'd love to hear your thoughts on that.
Well, I've actually run into a lot of problems on this exact issue. 208 works as long as that's your minimum. I've seen a lot of stores where they're in older areas. I'll go in and read 208, but then I get complaints of valve chatter or noisy pumps or just random things. And it took me forever to go in and find out that at certain times of the day, they were only getting 201. So you gotta be careful with 208 is an acceptable number, but as long as it's like your minimum. And you also need to follow your manufacturing specs is my big thing. Some will say 209, 210, whatever is minimum. And some will go as low as, I think I've heard as low as 204 from one manufacturer, but don't quote me. I'm not going to say who it is. So.
Okay. Sorry, go for it, Mike.
Electricity is like water. So you've got water flowing to the shower, and then someone flushes the toilet, the water pressure drops. So if you've got an espresso machine, the heating elements are on, you're drawing 208 volts, and then there's a big baking oven comes on, and it's close to the same circuit. That's going to create this excessive load, and it's going to drop the voltage everywhere. So that low voltage of 200 volts that's messing with the machine may not even happen while you're there, but it's happening at some point. In that case, you can actually put a buck and boost transformer on it and take it up to 230 and be safe. But that's a whole other issue.
Okay, Mitch Asbeck asks a question, and Caleb Leach also makes a valid point. His question is, what's the best way to deal with a machine that is hardwired? And then Caleb adds a valid point, because I think we all see this with convention centers and hotels. How do you handle it when the customer demands that you hardwire it? So let's deal with Mitch's first.
I'll jump in. So whenever I get a customer demanding hardwire, I actually tell them that they need to have the electrician present. I will talk with the electrician, talk him through what I need done, have him hardwire it with the breaker off, and then once he's got that done, I'll let it start up. But I mean, I know some hotels, it's just a requirement. You can't get around it. So I'd like to hear Michael and Matt's on this.
If the customer requires it, you're going to end up spending a lot more time in the location, going back and forth to the circuit panel. If you can't convince them that unplugging a machine actually has a benefit, there's not much you can do. I'm adamant about it because I try to be as persuasive as I can. Hardwiring a piece of equipment like that, it's just too risky to me. It's carrying a lot of load. It's usually out front where people can actually use it and see it. You can't protect it from customers generally. You can't protect it from users. The ability to unplug a machine is important. I know that in a convention situation, they're like wiring things together with wire nuts and taping the hell out of it all the time. But that's like a one-off deal. when I was doing trade shows, I got in the habit of bringing your own power. You know, I had a circuit breaker panel with breakout cords and everything all for all the equipment, and I said, here, give me a 60 amp 240 volt, you know, 4-wire hookup, hook it up to this big pigtail, and I'll take care of everything else. It was also a lot cheaper. You're not paying for 6 different services for a booth.
So, gentlemen, I have something to add to that. Apparently,
Okay.
everybody has my phone number. I just got a comment. 208 and 128 is rating for NEC for commercial kitchens. The panel is going to have 4 wires plus ground. 208, 120, 120 neutral plus ground. It's not legal to hardwire a machine. It's also not safe. Tech should walk away from the job. Not legal per NEC and UL. You guys are blowing up my phone right now. Thoughts?
Awesome.
I want to
Good
move on to
hear.
the next question.
Customers are generally stupid.
Ooh, we're going to hear from Don on that one.
Well, I'm going to
Customer's not
jump
always
in.
right. Customer is merely the customer.
If what's the best way to handle it then? If the customer says, "I want it hardwired," or you show up and the machine, there's a hardwired machine. Like, what in your experience, Michael? What would you have done with the customer at that point?
I've never had a case with a customer that was that insistent.
Okay.
You know, it kind of reminds me when I was tending bar. The restaurant that I had, we didn't have a well, and someone came in and asked, "Well, what's the best bourbon that you have?" And I said, "Well, if it's not your first bourbon of the evening, I would say Baker's is probably the best bourbon." And he goes, "Awesome, I'll have a Baker's and Coke." And I looked at him and I said, "No, you won't." He says, "I will pour you a Baker's and I will pour you a Coke. And when you get to the table, that's on you." So my attitude is kind of the same with the with you know, with hardwiring the machine. You know, it's like, you know, here's the pigtail. Get your electrician. If he's okay doing it, even though the code is pretty clear that you shouldn't, and I'm pretty clear that you shouldn't, and you're clearly, as the owner, the expert, you know, that's on you. I'm not, because you can't hardwire it. You cannot go into an outlet. An electrician is going to have to do that.
So
Your hands are tied anyway.
Darren Gordon has a question: does Matt have an opinion?
Does Matt have an opinion?
I don't know who Darren Gordon is. He hasn't texted me yet, so he doesn't have my number. So his question literally is, does Matt have an opinion? And I want to get away from this hotel thing because we have a lot of really good questions. And Kurt, I just emailed, we're going to be late for our next meeting. So Matt, do you have an opinion? And then we're going to move on to the next question.
Yeah, I do have an opinion. And I agree with that. I think the hard thing is that I've ran into instances where, and granted, a lot of times the major portion of my work that I do, we don't really run into that because I handle a lot of commercial account type items. So, I mean, we're on point with all of that because we have to be. But now, if I've helped out friends or anything to that extent, setting stuff up, like I can understand financially from a standpoint, like if you're running into a situation as a customer and you're like, well, this is what we have, this is what we've been given, this is not exactly how I would have ran it, but this is what we have, and cost effectively this makes sense. I get that from a cost standpoint, like you don't want to sit there and pay an electrician to come back in and do it the way that it needs to be. But the reality is, if you know exactly like what everybody is saying here, like what the expectations are technically and legally, then you have an argument to make, and you have to put it down and lay your groundwork down for what is supposed to be done right. And I don't think you should try to compromise in any way, shape, or form for your safety and for the safety of the store and anyone else associated with it.
Thanks, Matt. Okay,
Since
Mark Roby
electrician
has
has to hardwire it, you can certainly put a plug in it.
And no more hardwiring, guys. We can spend the next 20 minutes. We've still got a lot of questions.
Right.
Mark Roby asks a really good question. If I find a melted plug, what typically causes that? And can I just replace the plug and assume that I have solved the issue?
That's where the technician side comes in. You've got to figure out what the amp draw of the machine is first. I mean, sorry, Mark, there's not a clear-cut answer on that one.
Okay. Generally speaking, the cause of a melted plug is a loose connection, because a loose connection or an oxidized connection creates resistance, and resistance is a heating element. If you look at all the brochures and all the technical stuff for heating elements on espresso machines, the Italian version refers to a heating element as a resistenza. It's a resistor. It's just a big ass resistor. So anytime you have something that gets really hot, like a plug or a connection or a solenoid's got a bubble on the side of it, that's because there was a connection that created enough resistance to make a little miniature heating element. And that's what melts plugs, that's what melts solenoids, that's what melts transformers. That's what, melts the ends of wires off of heating elements, for example. So it becomes its own heating element. The most likely cause is a loose connection. Another cause is an oxidized connection. If it's in an environment where there's, a lot of ocean air and it's exposed to the elements. That's why once a year, if you're doing a PM, it doesn't hurt, since you're pulling the plug on an espresso machine before you service it anyway. Take 5 minutes, pull the plug apart, reseat all the connections, make sure they're tight, and then plug them back in.
Caleb Lee.
Don will be very happy I said that.
Yeah, Don. Yeah. No comment on our questions and comments. Caleb Leach asks, why is 208 considered more efficient than 240? It seems like less amps at higher voltage would be efficient. Any takers? Bueller?
Okay. Generally, I like high voltage. Espresso machines love to live at 240, 245. They heat up faster. You're delivering more power more efficiently to the elements. You run less risk of voltage dropouts. It's pretty rare that you'll get like 280 volts to a machine, but typically, 240 is a very happy place. The reason why you can't get 240 everywhere is because a lot of commercial buildings are set up as three-phase. And the way three-phase works is instead of that sine wave being 180 degrees out, you actually have 3 legs, and each one is 120 legs out, 120 degrees out. So the peaks intersect at different places. So in a three-phase application, or even if you only have single phase to your building, it might be in a commercial area where they've only got three-phase set up. You're only going to get 208 volts, period. Okay. You can't get more. It's not something you get to vote on unless you plug in a buck and boost transformer. But when you do that, you have to increase the circuit size feeding that buck and boost transformer, because you're drawing more amperage than you counted on.
Thank you. Nathan Van Dusen has another question. If a space has been built with a 30 amp outlet, can I install a 20 amp machine on that outlet without problems?
Yeah.
Okay.
Absolutely.
So manufacturers.
One of my on the last question, one of my people blowing up my phone is, it's not less amps at higher voltage in a resistive load. It's more amps with increased voltage. It has nothing to do with phase or AC. You could supply DC voltage and it would be the exact same result. This goes back to the amp question. Comments? Matt, do you have an opinion?
I still find that funny. In regard to this, I need to contemplate that because I had the previous one in my head, but now that we've been talking about my opinion in general, I've lost that too. So give me a second and I'll find an opinion on that specific question.
Let's move on. Let's keep moving forward because we're getting a lot more questions here. Let's see, where was Mark? Had a really good question. Mark had a question regarding amps and breakers. If I have a 2-pole breaker at 30 amps, does that mean I have 30 amps total, or is each leg of power allowed 30 amps before it trips? Meaning, can it pull, in theory, 58 amps total, 29 on each line? Mark, more complicated questions, please. Mike, Matt, Mike, let's start with you.
No, okay, it's a 30 amp breaker per leg but it's 30 amp referencing neutral, but referencing each other, it's a total of 30 amp because they're actually working together. So you've got the 2 110 lines feeding 240 volts. A 30 amp breaker will handle, at 208 it'll handle like 24, 25 amps. So no, a 30 amp breaker will handle like, well, 30 amps, so 6,000 watts, 6,500 watts.
Okay.
You can't treat them separately. You have to treat them together because you're actually utilizing both.
Okay. Mike Kahn has a good question. In the rest of the world, 380, 400 volt three phase is the normal supply for espresso machines. Why do we not use three phase machines in North America?
We
Kurt,
don't
do you have
have
an opinion?
it.
They're not wired
Okay, if you
for
think
it.
about it though, even in Europe, okay, even in Europe, those 380 volt machines, only the elements are operating at 380 volts. Everything else is operating on 200, 220, 240, because they've got a neutral and they're all referencing neutral. All the motors, all the components, all that stuff, they've all got capacitors on them. They're all operating in single phase, one hot against a neutral. Only the elements are operating in what we call three phase. And really all they're doing is they're providing an additional phase. They're breaking out the heating element to make it a little more efficient. You get some efficiencies in three phase on resistance, but it's not huge. Resistance is resistance is resistance. So if you, no matter how much, how we're throwing more voltage at it doesn't make it a hotter element. So for example, if you've got a 2,000 watt 110 volt espresso machine sitting on the counter and a 2,000 watt 220 volt espresso machine sitting on the counter, provided that the wiring is all good, they're going to heat up at the same rate because 2,000 watts is 2,000 watts. If you're feeding more voltage to an element than it's rated for, it will heat up faster. But voltage by itself doesn't make the machine, whether it's 110 or 220 or 380 or 480, whatever it is, it doesn't make it necessarily better. It just has to deal with what kind of wires you have to feed to it and what the circuit breaker panel looks like. But yeah, I mean, there's nobody here outside of an industrial application that has 380 volts.
Okay.
You go to
questions.
war with the army you have.
Okay, let's dial some of these questions a little back to the subject, which is what a new tech needs to know about electrical. Matt, when you're training a tech about electrical stuff, where do you start? You got basically a new tech who has a basic understanding of a meter. Where would you start? Where would you send them to learn?
Yeah, that's a good question. And that's something that, I've been working on trying to get some formalized documentation, kind of like what, Michael here was already kind of putting together, but just finding a way to talk through the basics of exactly what the differences are between voltage, your power and your current, and trying to figure out a way to correlate that in a way that makes sense. Having visual diagrams, and everyone's different. So somebody might learn very visually, somebody might have to learn hands-on. And that's the challenge with understanding this, is that sometimes you have to figure out how everybody operates as a new technician or how you learn yourself. For me, I love visuals. I love being able to create visuals and I understand them. That's what makes sense to me. So typically I'll take sine waves, explain that, DC current, take that and compare the sine wave to the DC current wave. Even though it's not really a wave, and then to start taking diagrams and looking at receptacles, just like we were looking at just a little bit ago. So I think just starting from the groundwork, understanding how voltage works, and then you can start diving into all these crazy fun questions with 360 plus volts supply and how that all works in the US and otherwise. But I think just getting to the groundwork, just here's what 110 is, this is what the wiring looks like at a 110 receptacle, here's what 208 is, here's the difference between those two, and start just understanding the rudimentary facts of that and having visuals on hand too.
Thanks, Matt. Kurt, your thoughts. You run techs like you and me do. Where do you start with techs?
First, I just figure out their learning style. Are they auditory, visual, or kinesthetic? Until I know that, I can't really do much with them. Because some of them, it's just better to have printouts that, as we're doing on-the-job stuff, they can just kind of go through their printouts and look at them as we're talking and working on stuff. Other guys, it's just I take my hands away from stuff and start just coaching them and just saying, look, when you're measuring from, L1 to L2, you're going to get this voltage, and explain the waves and everything. And then the visual guys or the auditory guys is just more, okay, here's the notebook. I'm going to start talking to you out loud and just have you write your own notes. And I'm using the kind of like what Michael has put together today. I just talk about the different waves, ground to L1, ground to L2, L1 to L2. So it's just all about finding out how they work or how they learn, and then just start very basically talking to them or showing them. I don't like them being hands-on unless I know that's the only way they're going to learn it right away. First, I'd rather them actually learn and understand what they're looking at.
Okay, thanks, Kurt. Mike, your turn.
When I used to do trainings years ago, if I had a whole day with technicians, I would generally take the first 2 hours and just talk about theory. Put a picture of the machine up. Here's the power. Here's the water. This is where the water goes. This is how machines work. This is how it's all connected. This is how things get hot. This is how temperature flow. Basically, try to cover the holistic system of what an espresso machine is. Because you can teach anybody to swap out a pump, but they don't know why they're swapping out a pump. So I'm trying to train the technician. I'm trying to teach them how to think about machines before I start getting into the weeds about this is exactly what's happening here and here and here and here. The biggest mistake that most technicians make is they just take a meter out and they check, a lead and check it to ground and say, oh, I've got power. Yes and no. Yeah, so knowing how to meter in the next seminar is going to be a good thing.
Yeah, and that the meter, it will be part of the Ask the Expert Pro series that will be released in March, you guys. And with part of that series, we will finish with a Q&A for all of our members, and that is for CTG members only. I have another question, because this is one that I've personally had difficulty in training, and I'm going to start with you, Kurt. How do you explain an open short to a tech who's new?
An open short? I actually just like using, I like using the elements, because I actually will show that a lot of times wait a minute.
Open short's kind of a trick question.
Yeah, that's fine. That just got me. I'm like, thanks, Hylan.
I mean, it's a disconnected wire.
Yeah, thanks, Hylan.
No, but here's the deal: is when you're explaining to text, it goes back to what Mike says, is grabbing a meter and going, well, that's fine. I mean, I've seen this happen a dozen times with text, and it's like, well, I've got power, but, and my best example is, and I recently had this, is the leaking element.
Yeah.
So it's like a new tech. As teachers, how do you explain to a new tech what it is? How do you go? You need to go deeper, and that's the best example that I could find where there's always a disconnect. I wasn't purposely getting you, Kurt. I was actually literally trying to figure out a way to explain this to techs.
Typically, it is that open, or the element that's open that is shorting out, is what I like to use, because when it's leaking into the water, as Michael explained earlier, the whole I think of it as a loose wire at that point. So I've seen too many elements where they're broken in half, and each side is shorting to the tank itself, just creating that energy, that heat in there. And you're asking a great question, because it's every person, you're gonna have to explain something a little bit different. And that's why I go with the method of train people 2-3 different ways. I like having all my guys go through multiple trainers, plus on the job with me, plus books. So you're asking a really hard question to answer, because it depends on the person again. To me, that's what it matters.
Matt, your thoughts?
No, I'd agree with that. I think it's really hard to explain, especially when we're doing ride-alongs, because the way that we train typically is that we'll run several weeks, and we'll have our new technician shadow an experienced technician just so that hopefully they can get a good understanding of a wide range of problems that they're running into, and they can get hands-on from a visual standpoint, at least, like this is what's going to happen. This is, but the reality is that we're not, even in that couple week time frame, you're not going to see every single crazy thing that happens. Actually, I remember as a new technician, like I spent several weeks with some great guys up in Michigan, and then I felt like I saw every single weird possible thing I could find as soon as I got in the field by myself. And like you can explain it all you want, but then understanding how that translates over in the real world is something different sometimes. So I think you kind of have to take it with each instance, and you just have to know what to look for. You have to have somebody in your back pocket that knows more than you do. And I think that was the biggest thing for me, was that I had a network of people that knew what they were doing. And I think this is what all boils down to for me, I think, is that going into it as a new technician, you're not going to have every single theory known. If you know the basics, understanding how things work mechanically, electrically, so on and so forth, and you have a good network, a good mentor to lean on that can maybe help you walk through some of those weird electrical things, like, yeah, that might be your best option right there, because you can know everything, but sometimes real world is a lot different than paper.
That's true.
Mike, before I start with you, we're going to wrap it up with that question. I want you to answer, but Mike Kahn has an interesting point. For a new tech, I will always reduce all components to being either a wire, element, solenoid, coil, or a switch, relay, contact, or touchpad, and teach them how to test them accordingly, which is a great point, Mike. Thank you. Michael Teahan, it's your turn. Stop reading Don's comments.
No. Whenever I'm approaching a machine trying to figure out what the hell's going on, I try to take a 3,000-foot view first before I start tearing stuff apart. Look at what it's doing, what the original complaint is, and try to develop a game plan before I pull it apart. If it's, if I'm not getting voltage where it's supposed to go, I'll start at one side and keep working back until I find it. Or I'll start at the beginning and keep working forward until I'm losing it. I don't usually just dive right in the middle unless it's something I'm familiar with. In the cases of heating elements, for example, you could drop a leg from the pressure stat, and if you're checking voltage to ground, you're going to get voltage on both legs of that heating element. And it's going to seem like everything is fine. I got 110 to ground on both sides. But what's actually happening is you got 110 going to one side who's passing through the element, coming out the other, and you're only referencing ground. That's why, in the case of heating elements, you got to disconnect some wires to actually know what you're doing, to actually get a real picture of what's going on. I use resistance a lot. I'll disconnect one side of an element or remove the bridge and check the resistance of all the coils to see if maybe I've dropped a coil on the element and that's why it's heating up slow. Or if I'm getting 600 ohms, that means I know I've got a fractured element or a melted element. If I'm checking continuity between points on a pressure stat and I've got 6 or 7 ohms between points, I know I've got corroded points. So a lot of people will use their voltmeter. I tend to use my ohm meter a little bit more because I think that kind of takes it down to what's actually happening with that specific item, whether it's a transformer, a coil, a solenoid, or whatever it is, as opposed to the voltage that's happening to the machine. Usually, the voltage that's going to the machine isn't the issue. Circuit panels are pretty good. It's the stuff inside the machine that interrupts the voltage, and for me, ohms kind of tells me a little bit more about that than anything else.
Gentlemen, it is a little after, so I'm going to wrap this up. I want to thank you for your time. For those who are watching and listening, we will take the questions and put them out to the group to answer, and we will also respond to some of the comments. I want to thank everybody for attending, and we will see you next week at 8 o'clock. Everyone have a great weekend, and thank you for your time.
Bye, everyone.
Thank you.
Thank you.